All right, everybody. So I apologize again for not being able to have class for period 7 yesterday. Yeah, I definitely had some important stuff to deal with. I had a bunch of money drained from my bank account, but I managed to fix all of that. So I'm happy that worked out. But anyways, so I'm gonna make a video about lesson 14 here, so you guys don't fall behind or anything. We can keep going. All right. So, but before we start the new material, I kind of want to summarize what we've learned from the old material now that we've passed exam one. So obviously exam one was all about integration, and there were sort of two main takeaways I wanted you guys to get from integration. Okay. So the first takeaway is that for applications, we split the problem into slices. And this, I call this a bunch of different things. I call them slices, chunks, cross sections. But essentially, you just break your problem up into little pieces. And then when you add them all together, that forms an integral. So this is typically how integrals are used in applications, or it's a good way to think about them. The second thing that we've learned from our time with integration is that integrals are hard. And this isn't really a joke, and I'm not really saying this because of like the past exam or anything. You probably noticed that integration is certainly much harder than differentiation. Like there are like pretty much if you could write down any function in terms of elementary functions, like the stuff we're familiar with from high school, we could pretty much take the derivative of all of those. But it's very easy to write down an integral that we can't do in terms of the functions we do in high school. So I gave this example on the very first day of class to introduce the course. So we have the integral of sine of x squared here. And if we wanted to write down the antiderivative of this, I wouldn't be able to do it. And we wouldn't be able to do it with any of the techniques that we've learned in class so far. Now, granted, we have learned how to integrate a lot more integrals than we knew before. So that's certainly good. And those integrals do show up pretty often. But there are still a decent number of things that we just don't know how to integrate. And it's not a matter of like going on to calculus 3 or beyond. Even if you ask the professional mathematicians or other people in the math department or anywhere, they're not going to be able to write this down, at least in terms of what are called elementary functions, the functions we're used to from high school, like trig functions, exponentials, polynomials, logs, etc. Okay, so what if we actually needed to know what this is for an application? Like what if we needed to work with the function sine of x squared? Well, fortunately, there is a way to get an answer to this question, but it may not be as satisfying of an answer as we would like. Like it might not just be a regular old function, but there is a way that we could do this. So what we're going to learn how to do in part 2 of the course. So part 2 is all about doing things like this. So I take my function sine of x squared, which on the surface is not a polynomial, and I could write it down like this: x squared minus x to the 6th over 6 plus x to the 10th over 120. And then we're going to have some other terms out here. And this will actually go on forever. So even though sine of x squared isn't really a polynomial, we can sort of approximate it as a polynomial. And if we wanted to, we can keep adding more and more terms to get a better approximation until we have infinitely many terms where this will actually be exactly equal to sine of x squared. So why would we want to do this? This looks pretty terrible compared to this nice compact form here. Well, the theme of part 2 is that polynomials are nice. So when we were in high school learning about algebra, probably one of the first functions we really focused on were polynomials. And these functions are really nice, particularly in calculus, because it's really easy to just do the power rule to integrate or differentiate those. So just like a regular polynomial, if I wanted to do this antiderivative here, then all I would need to do is just do the power rule on each one of these terms. So what would happen is I would get x cubed over 3 minus x to the 7th over 7 times 6 plus x to the 11th over 11 times 120 and then that would go on forever, and then we would, of course, have plus C. Now, you might be thinking, okay, well, I guess we technically got this answer here, but what does that do for us? Well, it turns out that in most applications, your compute, like most applications in math nowadays, end up becoming going on a computer in some point. And when your computer imagines functions like sine or cosine, it doesn't think of them as sine or cosine. It thinks of them as one of these really long polynomials. So entering an answer like this into a computer, if you had this for an application, would be just as useful as entering in, say, like a more normal function here. So having answers like this is actually just as useful as having like a traditional formula for your answer. So what we're going to focus on now is we're going to focus on turning functions that aren't really polynomials into these infinitely long polynomials here. And we're going to see what we can do with those. So these infinitely long polynomials here are called power series because they have a bunch of powers of x and they're added together. These are a special example of things that we're going to learn about called infinite series, where we have a bunch of numbers added together. But before we can get into either of those things, we need to learn about something else first. And that brings us to today's lesson, lesson 14, where we're going to talk about something called sequences. Okay, well, what is a sequence? What are we going to be talking about here? The sequence is an infinitely long list of numbers. That's literally all it is. It's just a giant list that goes on forever, and it has a bunch of numbers in it. Let's see some examples of this. So one example would be this sequence here: 1, 2, 3, 4, 5, 6. And I bet you could probably guess what the next one's going to be. It's just going to be 7, and then this keeps going on for forever. And the pattern for this sequence is that the numbers just keep getting bigger every time we move one more place in the list. This is an example of a sequence. Here's another example: 3, 3, 3, 3, 3, 3, 3. And you can probably guess what the next one in this would be. It'd definitely be just another 3. And we keep just listing a bunch of 3s forever. The sequences can repeat numbers, and they can be made up of only one number if you want to. But nevertheless, this is still just a list of numbers, all of which are going to be 3. Here's another example: 1, -1, 1, -1, 1, -1, 1, and then, of course, the next one's going to be -1. So it keeps flipping sign, but being 1 the whole time. So this is a sequence here. This is going to be called an alternating sequence, and we'll talk about that in a little bit. And we notice that we change sign when we move forward in a term of the sequence. All right, here's another example: 1, 1/2, 1/3, 1/4, 1/5, 1/6. So this one's very similar to the one up here, except we have 1 over all of the counting numbers. And notice that these are getting smaller and smaller and smaller, and they're getting closer to 0, the bigger our denominator is going to be. And also this shows that we can have fractions as part of our sequences. Now let's take a look at this one. We have 1, 2, 4, 8, 16, 32, 64. This goes on forever. This one is just having a bunch of powers of 2s. And whenever we have some kind of exponential function that's making our list, this is going to be called a geometric sequence. And this will show up a decent bit. Let's take a look at this list here: 2, 3, 5, 7, 11, 13, 17, 19. And this keeps going on forever. Now, for this one, it might be a little bit more difficult to recognize what's the underlying pattern here, because it mostly seems like a bunch of odd numbers, but then we have 2 at the beginning. But then we're also missing some other odd numbers. We're missing 9 and 15. So what's the pattern here? It turns out that this is a list of prime numbers. And remember, a prime number is a number that's only divisible evenly by 1 and itself, as long as you're looking over the whole numbers. So this is a sequence of prime numbers here. And then finally, here's one more sequence I'll give you guys. We have pi 17 e to the 2020. We have 4.444443. Oops, negative. I want that to be a negative there. Then we have 0, and then we have 6. And unlike the other ones, it's really difficult to guess what the next one would be here, because this sequence doesn't really have any rhyme or reason. Yet it is still considered to be a sequence because it's an infinitely long list of numbers. And in whatever mad way this is continuing, as long as it goes on forever, it's going to be a sequence. And we're really not going to be focusing on sequences like this. We're going to be mostly focusing on guys that are a bit more like this, that have some kind of underlying pattern. But it's good to recognize that all a sequence is just a list of numbers, an infinitely long list of numbers. And these numbers can even be like irrational, like e to the 2020 and pi, things like that. So you can use any number you like. It just needs to be an infinitely long list. Okay, so what we're going to do with these sequences is there's a lot of different, there's a lot of terms to identify and classify different sequences. Now, the most important distinction that we're going to make with our sequences is whether they converge or diverge. So a sequence converges if it gets closer and closer to a particular number as the list goes on. So all that means is this, that the list seems to be settling down towards some particular number. So like, for example, in this case, this sequence obviously converges, and the number it's settled down to is 3. It's getting closer and closer. Well, I mean, it already is at 3 forever. This would actually be an example of another convergence sequence, although this one doesn't actually include what it converges to in the list. So these numbers are getting smaller and smaller as we go along, but they'll never be negative. These numbers are always positive. So then what does that mean? That means that this sequence will converge to 0. But 0 won't ever be in the list, but that's okay. It just needs to get closer and closer to a number. It doesn't actually need to be in the list of numbers itself. Okay, so that's what converging means. And a sequence diverges if it goes off to plus or minus infinity or doesn't settle down to a particular number. Okay, so let's go back to this list up here and think about which of these ones might diverge. So this first one up here, even though it has a nice well-defined pattern, this one's certainly going to diverge because these numbers are just going to keep getting bigger and bigger and bigger. They're not going to stop and settle down near a particular number. So these ones would diverge by going off to infinity. And then we have this example right here where we have ones and negative ones, and they keep alternating forever. This sequence will also diverge, but it'll do so a bit differently from the one up here. It won't go off to infinity. These aren't getting huge. It just doesn't seem to be settling down to a particular number. It's not approaching any one number. So this sequence would also be considered to diverge here. So as an exercise, let's go ahead and label which one of these are going to converge and diverge. So we already talked about a lot of this. So let's see here. So this one's going to diverge. This one's going to converge. And when we say a sequence converges, it converges to a specific number. So this one's going to converge to 3. That's the number it's getting close to. This one's going to diverge, but again, it's going to be different from the way this one diverges. This one converges to 0, as we discussed earlier. This one's diverging, it's going off to infinity even faster than this one is up here. So this one's going to diverge. In the same way, this list of prime numbers is going to diverge as well because there are infinitely many primes, but they just keep getting bigger and bigger. So this one's going to diverge too. And finally, it's not clear at all what this one's going to do. It's kind of like a completely random sequence. So for all intents and purposes, this one's going to diverge as well. It's not really settling down to a particular number. Okay, now the way we determine whether these converge or diverge is we kind of just looked at them and we saw what the pattern was and what they were doing. But sometimes it's not entirely obvious what's going to happen based on the first few terms. Like it could have a few misleading terms where it's getting really huge, for example, but then it might end up settling down after the first few terms that you write down. So how are we supposed to know for sure whether or not these sequences are going to settle down to a particular number or maybe oscillate or go off to infinity? Well, this is where we write down formulas for a sequence. So a good way to tell if a sequence will converge or diverge is to write it as a formula. And so when I say a formula, I mean a formula, oops, sorry, I don't have anyone to remind me to push the page up. So when I say a formula, I mean as a function of a variable, and traditionally this variable is called n. Reason being is that we're only going to have whole numbers as input. So I'll explain that more in a second. To write as a formula as a function of n and take the limit as n goes to infinity. Now, what does this n represent? The n represents how far in the list something is, or its place in the list. So for example, let's try to find formulas for all of these sequences that we had up here. Now, it might not always be possible to find a formula, but we're at least going to try with these. So for example, let's see here. So the first one is 1, 2, 3, 4, 5, 6, 7, and that goes on forever. So it seems like the first number in the list is 1, the second number in the list is 2, the third number in the list is 3. So what's our formula going to be? Well, our formula is just going to end up being n. Whatever place we are in the list, like the first, second, third place, that's just exactly what the number is going to be. Now, let me explain this kind of terminology here. There's sort of an analogy between this and the way we're used to looking at functions. So traditionally, when we write down formulas, we usually write it down f as a function of x. I guess the matching x formula would be this. So x and n are both the variables, but unlike these functions right here, instead of putting in a parentheses next to the function, we put it as like a little subscript. So note this is supposed to be smaller and to the lower right of our symbol. And traditionally, we usually use f for our functions, but it's also customary to start a for sequences here. So this is like the formula or function name. So rather than using f of x, we're going to use a of n. And kind of like if we already used f, we're going to use g. If we already use a, we're going to use b. Or maybe if I want to have like a different variable like y, then m might be a different variable here. But the key thing is to remember that n is your place in the list. So that's why the formula for this one will be a sub n equals n, because whatever place we are on the list, that's just what the number is going to be. All right, let's move to our next example here. This is the sequence with all of these 3s that go on forever. All right, well, let's see if we can write down a formula for this one. Well, it seems like no matter what place we are in the list, the first, the second, the third, the fourth place, no matter which place we are in the list, our number in our list is always just going to be 3. So a sub n equals 3. And this is also called a constant sequence, a sequence that always has the same number no matter where we are in the list. This is a pretty easy formula to come up with here. All right. And then let's go on to the next one here. The next one was 1, -1, 1, -1, 1, -1, and so on. Now, this time I'm going to do something a little bit different. So normally you might expect, okay, this will be the first place in the list, this will be the second place in the list, this will be the third place in the list. But as we're going to see in future classes, it's often convenient or even necessary to start our sequences at 0 instead. So this would be the 0th term, this would be the first one, this would be the second, the third, the fourth, etc. So let's try to make this formula having in mind that we're starting at 0 here. So a sub n this time, well, let's see, it seems like whenever we have an even number, our 1 is not going to have a negative here. Whenever we have an odd power, an odd place in the list, it's going to be negative. That suggests to me that my formula should be -1 to the n. Because when you raise -1 to an even power, it's going to be positive, and when you raise -1 to an odd power, it'll be negative. Okay, now one question that immediately arises is, okay, well, I started the list at 1 here and I started it at 0 here. how do I know which one it's going to start at? Well, one way you could identify that if it's not obvious from some other kind of context is you could use this notation. So if I wanted to specify that this begins at 0, I put parentheses around my whole formula here, my name for it, and then I say n equals 0, and then I put an infinity on here. That means that this list starts at 0 and it goes on forever. If I wanted to do that back in this one, for example, I'd put the parentheses and then I'd have n equals 1 to infinity. So if it's not clear from context, and we'll talk about what that means in a future lesson, you could use this notation to identify whether you want to start at 0 or 1, or you could even start at a different number too. Like sometimes we may begin sequences at 2 or 5 or whatever. You can start at whatever number you want so long as you mention where you're starting it. And note that this sequence formula would actually be different if I decided to begin this at 1. I'm so used to doing integrals, I draw the evaluation line there. So n equals 1 to infinity for this one would be negative 1 to the n plus 1. Because this time I want all of my odd numbers. So this would be the situation now. I would want all my odd numbers to give me a positive 1, and that would happen with this. And I want all my even numbers to give me a negative 1, which would also happen with this. Also, another acceptable way to write this is negative 1 to the n minus 1. Both of these are totally correct, so you can use whichever one you like. All right, let's see. What else do we have here on our list? We have 1, a half, a third, a fourth, fifth, and so on. I think it might be a little bit easier to write this formula if I started at 1. This is the names of all the places in the list. So it seems like whatever place I have in the list, that it just appears in the denominator of my numbers here. My a sub n will simply just be 1 over n. If I wanted to specify this one starts at 1, then I could do so right here. I think it's a little bit more obvious. This one doesn't start at 0 because you definitely can't plug in 0 here. But just to be safe, I would write it like this. And if I did want to start this at 0, then I would have to rewrite the formula a little bit. It would have to look like this instead. So for example, the 0th term, which would be right here, needs to be 1 over 1. The first term needs to be 1 over 2. So I always need to bump up what's in my denominator by 1 if I did need to start this at 0. All right, what else do we have? 1, 2, 4, 8, 16, 32, etc. All right, so the formula, I pretty much mentioned this one earlier. This is going to be 2 raised to the nth power. This one's going to be a bit more convenient to start at 0 because I have 2 to the 0th power here, 2 to the first power here, 2 squared here, 2 cubed, and so on. So I'm going to start this one at 0. If I wanted to start this one at 1, I could have the same formula. It would just be 2 to the n minus 1. All right, the next one, let's take a look at this. We have 2, 3, 5, 7, 11, 13, 17. So we agreed that all of these were the prime numbers. All right, so let's see. So let's try to write down a formula for the nth prime number. So this would be like the first prime number, the second prime number, the third prime number, the fourth prime number, and so on. But unfortunately, there actually really isn't a formula to just automatically give you the nth prime number. Like for example, if I just wanted to immediately compute what the millionth prime number is, there's no nice little formula that looks like this that can give me that. So there really isn't going to actually be a formula for this one here. And it's actually kind of good that there isn't a formula for that because a lot of our computer cryptography is based on finding really large prime numbers. So if you could just have a nice little formula that will give you arbitrarily large prime numbers, then that wouldn't be very good. You'd be able to hack into computers a lot more easily. So it's actually kind of a blessing we don't have a formula for this one. And finally, I'm not even going to write this down, but like that random sequence that I had earlier, that obviously doesn't have a formula either because that was essentially just a bunch of random numbers. All right, so the moral of the story here is that it's good to write down a formula so we can see what happens in the long run, which might not be obvious from looking at the first few terms here. Okay, so normally I would leave you guys to practice this, but since it's just me, I guess I'll do this problem. So practice problem 1. So I want you to come up with a formula starting at n equals 1, so I'm restricting you to start there, or the sequence that looks like this. 1, -2 over 2, 3 over 4, -4 over 8, 5 over 16, and so on. So let's take a look at this and let's try to come up with a formula kind of like we did for these patterns up here. All right, now this one, it looks like the pattern's a little bit more complicated than what we've done before, but the best way to come up with formulas for these is to kind of break the pattern up into pieces. And this is going to be something we're going to be doing a fair bit later. We kind of look for each thing that's going on in our list here, and we try to incorporate each piece of the pattern one at a time. All right, so I said I was going to start this at n equals 1, so I guess I'll specify that right here. And let's take a look at this. So I could view this 1 really as a 1 over 1 if I wanted to. Now let's look at the numerator. So I have a 1, 2, 3, 4, 5. Okay, well, it seems to me that whatever place we are in the list, if we start at 1, that's just going to be what the numerator is. It seems like we definitely have an n there. I guess it goes without saying that this is going to be a fraction since almost everything in here is a fraction. So it's going to be n over something. Let's see, what do we have on the bottoms? We have 1, 2, 4, 8, 16, etc. So this should look familiar. This is our list of powers of 2 that we saw earlier. But the thing is, if I start with n as 1, then 2, and then 3, 4, and so on like that, like the problem asked me to, these powers of 2 are going to be too big. Like this one should be 4 if I use this. This one should be 8 if I use this. So I need to kind of knock them down one so they're the right power of 2. So this bottom will be 2 to the n minus 1. That way, for example, if I looked at like the third place in the list, I have 2 to the 3 minus 1, which would be 2 to the 2, and that would give me 4 right here. So sometimes you may need to adjust by adding or subtracting here to get it to match up. And then there's one more thing that's going on with this. So we have a positive, a negative, a positive, a negative, a positive. So it seems like it's flipping sign every single time. Whenever we want to have our sequence flip sign every single time, we put -1 to a power in our formula. Now, typically it's going to be -1 to the n or -1 to the n plus 1. Now, if I made it be -1 just to the n, I'd plug 1 in for that for the first term, but I would have -1 to the 1, which would be -1. And then I would have a positive for this and negative for that. So it'd be completely backwards. So I'm instead just going to make this -1 to the n plus 1. And then all of my signs will be correct for these. So make sure that your signs are correct, not backwards. And you may, again, need to just adjust your indexing. And there we go. It seems like we've taken care of everything that at least appears in this pattern so far. So this is going to be our formula for our sequence right here. Okay, now what was the whole reason why we were doing this again? Why did we need to know these formulas? Like it's fine to write out in a list, but why are we having these formulas? Well, this is going to lead to the second practice problem, which again, I guess I'll do. So does the sequence from the previous problem converge or diverge? And here's an extra part. If it converges, what number does it converge to? Okay, so remember, if a sequence converges, it gets closer and closer to a specific number. So there should be, if this does converge, there should be some specific number that this gets close to. Now, the whole reason why we write down this formula is so we can use this method for finding what happens. So I said earlier that if we take the limit as n goes to infinity of our sequence here, whatever our formula is going to be, then that is going to let us know if it converges or not. So if this limit does not exist or goes off to one of the infinities, then it's going to diverge. But if it ends up going to a particular number, then it's going to converge. And reason being is that this limit is effectively kind of seeing what happens as we go really far down the list. And that's what I said we needed to do if we want to know if something converges or not. Converging is what happens in the long run. All right, now we have this guy right here. So notice that we have effectively a polynomial on top, like n to the first power. But then we have an exponential function on the bottom. All right, so what's going to happen with this? Well, the top is going to go to infinity because n goes to infinity as n goes to infinity. But we also saw earlier that the powers of 2 also go to infinity as well. So what is this going to be? Is it just going to be 1? Are they going to cancel out? Will this have anything to do with it? Well, this is where we need to become familiar with what's called the hierarchy of functions. You probably noticed by now in your mathematical career that there are a lot of different functions that go to infinity as their input goes to infinity. But the thing is that some of them go to infinity faster than others, and that's going to be crucially important for looking at limits like this. So traditionally, what's lowest on the hierarchy of functions are logarithms. So if we have like ln of n, or some kind of logarithm, this technically does go to infinity, but it does so very, very slowly. But this would go to infinity. The way we kind of differentiate between multiple places on this list here is we have this kind of double inequality, which means this grows faster to infinity. This one. What would come next on the list? It'd be n to some kind of power, as long as that power is positive. So effectively, this is going to be polynomials or power functions if they're maybe not a whole number power. So these go to infinity as long as our power is greater than 0, and this will go to infinity faster than log does, no matter what this power is. So this could be like 0.01 or something. This will still grow to infinity faster than this does. All right, and then what comes after this on the list? Well, if we have some fixed number raised to variable power, where this time we need this bigger than 1. So these are going to be exponential functions. And our most common example of this is e to the n, where e is 2.7, like that. So these will go to infinity even faster than these. Even if we have like 1.1 to the n, that will eventually go to infinity faster than like n to the 1 billion power. It doesn't matter how high this power is, this will always eventually beat it out, so long as a is bigger than 1. Now, in a few minutes, I'm going to talk about some things that appear even higher on this list that you may not be familiar with. But for now, we're going to kind of keep it like this. So back to this problem up here, the way this table works is that if something is lower on the list up here and higher on the pecking order down there, then our limit is going to be 0. And that's exactly the case here. We have effectively a polynomial power function on the top and an exponential on the bottom. Now, if it were the other way around, let's say I had like my exponential up here, my polynomial down here, then it would go to one of the infinities. And actually, it wouldn't be able to decide which one to go to because this would keep oscillating. So that limit wouldn't exist in that case. So if we have the lower one on the top, it's going to go to 0. If we have the higher one on the top, it's going to go to some kind of infinity or not exist. All right, so we saw that this one converges here, and it converges to whatever we get out of this limit. So the numbers in this list are going to keep getting closer and closer to 0. Now, you might be like, even with this example, you might be like, okay, well, yeah, that's pretty obvious that this is going to go to 0 because these are growing, but they're not growing as fast as these. But in the future, we're going to come up with sequences that are kind of really non-obvious from the first few terms what it's going to do. So this is ultimately going to be our way of looking at sequences. All right, so let's see here. Let's do some more examples of this just to get some practice. Okay, so my next example here is, let's say we have a sub n is 4n cubed plus n squared plus 1 divided by 3n to the 5th plus 16n plus 2. And we want to know if this one converges or diverges. That's what we want to know. And if it does converge, what number will it converge to? Well, just as before, the way we're going to look at sequences now, we want to see if they converge or not, is we're simply going to take their limit as n goes to infinity, or as we go super far along in the list. Now this right here, this is a rational function. Now you may remember from Calculus 1 about how limits for infinity work with rational functions. There are kind of 3 scenarios with this. If the degree of the top is greater than the degree of the bottom, then it's going to go off to some kind of infinity, like plus or minus, depending on what the coefficients are. If the degree of the top equals the degree of the bottom, then it's going to go to the ratio of leading coefficients. What do I mean by that? Let's say these were maybe both n to the fifth right here, then this limit would end up going to 4/3 in the ratio of their leading terms. And note that these guys don't really matter. And then on the other hand, if we have the degree of the top less than the degree of the bottom, then this is just going to go to 0. So it's kind of like infighting in this hierarchy of functions. So within kind of this area right here, n to the a is less than n to the b if a is a lower power than b. That's essentially what this is talking about here. All right, so in this case, we clearly see that the degree of the top is less than the bottom. So we know that this converges, and it converges to 0. Okay, let's take a look at the next one here. I have a few for example 3. Take a look at b sub n is 2 to the n over n to the 100th power. All right, well, just as before, we're going to look at a limit for this. Okay, and now let's see here. So we have an exponential function on the top and a power function on the bottom. So if we go up to the list here, we see the power functions end up being weaker than exponential functions. Since our more powerful functions on the top, this is going to go to positive infinity and it's going to diverge. Now you might plug in a few numbers here. Like let's say we plug in like 3. We're going to have 2 cubed, which will be 8 up here. But on the bottom, we'll have 3 to the 100, which is an absolutely enormous number. And so this will be super close to 0. So if you wrote out the first few terms of this, you might be like, oh, this is obviously going to be 0. Like this is huge. That's tiny. But in the long run, if we keep going, this will eventually become larger than this. And the reason is when we're multiplying more numbers together. Like if we have 2 to the million over a million to the 100, even though a million is a bigger number, we're only multiplying it by itself 100 times. But if I do 2 to the million, I'm multiplying 2 by itself 1,000,000 times. So eventually this will win out. All right, our next example here, I guess I'll just cut to the chase and just write it in the limit to save a little time. So we're looking at the limit as n goes to infinity of e to the n, and it is divided by this guy right here. We have n and then an exclamation point. So what the heck is this? We need to know what this is before we can figure out if this converges or diverges. By the way, I gave this the name Cn. So if you haven't seen this before, this is pronounced n factorial, or really whatever this is, factorial. And how does this work? Well, n factorial is n times the next lower number, n minus 1, times n minus 2, and then times n minus 3. So we just keep going down through these whole numbers until we get to 3, and then we multiply by 2, and then we multiply by 1, and then we're finished. So note that this only works, at least for now, with whole numbers. So you can really only have a whole number factorial. And that's totally fine for these sequences because our n here will always be a whole number. So that won't be an issue. Okay, so it seems like we're multiplying a bunch of things together, but then remember, exponential functions are also multiplying a bunch of things together. So which one ends up being stronger here? And it turns out that factorials end up beating out exponential functions. So since our more powerful function is on the bottom in this case, we're going to end up with 0. Now, why is that? Well, on the top here, we are indeed multiplying by more and more numbers each time. But on the bottom, not only won't we be multiplying by more and more numbers as this gets bigger, but the numbers we're multiplying are getting bigger too. That's why these end up being bigger than exponential functions in the long run. All right, let's look at one more example of this before we move on to something else. So I'm going to look at the limit as n goes to infinity of what I'm going to call dn. What is that? That's going to be the natural log of 3n plus 1 minus the natural log of n. All right, now, all these other cases, I could kind of just look at the hierarchy of functions or plug my limit in right away. But if I look at this, if I plug in my infinity right away, it'll be infinity minus infinity, which is called an indeterminate form. We don't really know what's going to happen with that unless we do some more work. So what I'm going to do to simplify this is I'm going to use log rules. I'm going to turn the subtraction out here into division on the inside of this. So this is the same function as that right here. Now, natural log is what's known as continuous. We haven't used that word in a while, but essentially what that means is I could put limits inside my parentheses here. And then finally, I'm essentially just looking at the limit of 3n plus 1 over n. We already saw what would happen with this. Since the degree of the top and bottom are the same, we look at the ratio of the coefficients here. This time our ratio is 3 over 1, so our limit will be 3. And then that means that our overall limit will be natural log of 3. So numbers in this list, as we keep going, will get closer and closer to natural log of 3, which is a number that's a little bit bigger than 1. All right, so there's some good examples of determining whether or not sequences converge or diverge. All right, now there's other terminology besides converging and diverging that will also be important for sequences. Not as much as converging or diverging, but they're still definitely worth knowing. So I'm going to kind of quickly go through these other terminologies here. Okay, so one adjective we can have for a sequence is increasing. So a sequence is increasing if the numbers always get larger or stay the same size as we go through our list. And here's like kind of a more compact way of writing this. So if we have an plus 1, that's always going to be greater than or equal to an. So since this represents a further place in the list, this number needs to be bigger than or equal to an. And I bet you can imagine what decreasing is going to be. I could write this exact same sentence, except I'm just going to say smaller instead. And this one would be where an plus 1 is less than or equal to an. Now, this is where there's some disagreement among mathematicians on whether this should be increasing or you should use a strict inequality here. So I would kind of erase the stay the same size part in this sense. And then same thing for decreasing. For our purposes, we're going to include the equal to here. I think it's going to be a little bit more convenient for us. Although there is a disadvantage to that. We know that, for example, the sequence of 3s that we had earlier actually ends up being both increasing and decreasing, which really doesn't make any sense based on the meanings of the English words, but that ends up being the implication here. So we do have some kind of weird consequence of that, but this will be more convenient for us in other ways. All right, so an example of an increasing sequence would be like that list of whole numbers. I think this one's a little bit more obviously increasing. An example of a decreasing one would be something like this: 1, 1/2, a third, a fourth, a fifth, so on, as these numbers are always getting smaller. And then we have this weird term, which you probably haven't heard of before, called monotonic. And what does this mean? It means that the sequence is either, so it's got to be one of these two things, always increasing or always decreasing. So if you're one of these two up here, so if you're either increasing or decreasing, then you're monotonic. So it doesn't need to be a specific one of those, but you just need to be either always going up or always going down. So a sequence that looked like this, for example, where the numbers are always going down, would be monotonic. This would also be okay, but something like this, for example, would not be monotonic. So both of these are monotonic, but something like maybe -1 to the n, that's not going to be monotonic because it keeps changing direction. All right, let's see. Our next piece of terminology is bounded. And what bounded means is that the sequence stays finite and doesn't go off towards infinity. Another way of imagining this is there's a maximum and minimum size or numbers in the list. Let's take a look at an example of something that's bounded. So I said this one wasn't monotonic. However, this is going to be bounded because we just have 1, -1, 1, -1, 1, -1. So the maximum size of a number in this list would be 1, and the minimum size would be -1. And there's absolutely no way that this is going off to infinity. So this one we would say is bounded, but on the other hand, something like an equals n, we have this. There may be a minimum size on this, it's not going to go lower than 1, but there is no maximum size for this. So it's going to keep going off and get bigger and bigger and bigger forever. So this would not be a bounded sequence, and this is referred to as unbounded. It can grow without end, or go negative without end. That also would be unbounded. All right, now here's one little fact that we might have occasion to use sometimes. So if you have a sequence that is monotonic, so either always increasing or always decreasing, and it's bounded as well, then we automatically know, without even looking at a limit or anything else, that that sequence is going to converge here. So if you have these two conditions, then you automatically get converging for free. And the intuition behind this is that if we sort of graphed our a sub n's, if you're bounded, you're kind of blocked off from getting too big or too small. So effectively what our sequence is doing is if it's getting bigger and bigger and bigger, it can't stop getting bigger because remember it needs to be monotonic. So in this case, it's going to increase the whole time. But at the same time, it can't go through this wall. So it's going to converge to something because it's kind of being forced to level off because of our wall from bounded. So we get this wall from bounded, and we get the increasing from monotonic. And we could also draw a similar picture if it happened to be decreasing. Like it'd be decreasing like this, but then there'd be a wall down here because bounded is both for above and below. So that's essentially what's going on with this. Note that the reverse is not true though. So just because you're convergent doesn't mean you're both monotonic and bounded. We'll talk about that in a second. All right, let's see. What other terms are going to be important? So we have 3 more that we'll end up seeing some use. So I mentioned this term before. An alternating sequence switches sign every term in the sequence. So every time we move from one number in the list to the next number in the list, we will change sign. So an example, probably the most basic example of an alternating sequence would be something like this right here. That's alternating. But something like this, we have like the same sign the whole time, that would not be alternating. But even something like this, where we have an is 1, 1, negative 1, negative 1, 1, 1, negative 1, negative 1, this would actually not be alternating either, because it needs to change sign every single term in order for that to work. So even though this does change sign and it does so regularly, it's not going to count as alternating. It needs to happen every term. All right. So a sequence is geometric if you get, let me say it this way. Each number in the list is a constant multiple of the number before it. All right, so what do I mean by that specifically? Well, let's take a look at a geometric sequence here. We have 1, 2, 4, 8, 16. So this was our 2 to the n sequence earlier. Now notice that the way I get the next term from the previous one is I multiply by 2. This is what I mean by constant term that I'm multiplying by. So I'm always multiplying by 2 here to get to my next term. So this would be a geometric sequence. That one's okay. We could even have something like, we have like 3, 6, 12, 24, 48. And even though this one isn't necessarily just a power of 2, we still get the next number by multiplying by the same number every single time. So this one would also be geometric. And finally, it doesn't just need to be times 2. We could, for example, have like powers of 3 or something like that as well. All 3 of these would be considered geometric sequences. All right, and then finally, one more definition. I guess I'll say this one's not going to be as relevant for this class, but if you do ever take differential equations, these guys will pop up. So I guess I want you guys to be at least somewhat familiar with this. So a recursive sequence is where the next element in our list, the next number, is defined based on previous elements. Okay, so what does that mean? Actually, technically, geometric sequences here are going to fall into this recursive category because they do depend only on what happened in the previous one. So here's an example of a recursive sequence. So we have an is going to be an minus 1 plus an minus 2. And maybe we start a0 as 0 and a1 as 1. Okay, so these numbers are kind of just there to get us started. So if I want to figure out what a2 is, for example, I would take a1 and put it there, and a0 and put it here. So my a2 is 1. If I wanted to get a3, that'd be a2 plus a1, which would be 1 plus 1, 2. And then to get a4, I would add a3 and a2. So what is this list going to end up being? This might look familiar to you. This is actually the Fibonacci sequence. And this is what's called a recursive sequence because the next number in the list depends in some way, in like some kind of functional way, on the previous numbers in the list. So the Fibonacci sequence would be an example of a recursive sequence. Again, not quite as relevant for us right now, but this is something you should be aware of if you ever take differential equations. All right, finally, let's go on to our last example here, and then I'll let you guys go. This video is already kind of long. So here are some kind of questions about our terminology. So these are sort of some hypothetical questions here. So what is an example of a sequence that is not both bounded and monotonic? And looking at the notes here, I think I meant to say convergent sequence. It's actually really easy to come up with something that's not both of these, but a convergent sequence. Well, so remember, it can't be both bounded and monotonic. So it can't be both of these, but it could be one of these. Now, let's think about bounded. So if a sequence converges to a number, that means it needs to settle down to that number and not shoot off to an infinity. So if you have a convergent sequence, if you know it's going to converge to something, then there's a limit on how big you can get, because you always have to either come back down towards your number or you have to kind of settle up at a number as well. So it turns out that if you have a convergent sequence, it already has to be bounded. So if we're convergent, we automatically have to be this one, meaning that we don't want to be monotonic. So what's an example of a convergent sequence? So a sequence that converges, but isn't monotonic, meaning it doesn't always go up or doesn't always go down. Well, we actually wrote down an example of that earlier today. Let's use our sequence that we had for our first practice problem. So we saw that this does converge, it converges to 0, but this is also not going to be monotonic because sometimes it's going to go up when we switch to a positive number, but then other times it's going to go down when we switch to a negative number. So this one's not monotonic because it changes direction as our sequence progresses, but it does converge. So it's not both of these. All right. So what is this, an example of a sequence that is bounded but not convergent? Let's think about this. So we just saw that convergent means bounded, but the other way is not necessarily true. So bounded does not necessarily mean convergent. And here's a basic example of that. Let's say we have this alternating sequence that we've been seeing quite a bit. Remember, this is just a constant flip between -1 and 1 right here. Now, this is certainly bounded. It never gets bigger than 1 or less than -1, but at the same time, this one is not going to converge. This would be an example of something that is bounded, but not convergent. And our final thing is to name an example of a recursive sequence, but we already saw that the Fibonacci sequence is an example of that. I'm sure that's something all of you guys have seen before. All right, well, that about does it for our introduction to sequences. So remember, everything I talked about today had to do with sequences. I briefly mentioned something called series in the beginning. I haven't told you guys anything about those yet. So everything I just said here applies to sequences or lists of numbers. Now, next time we will be learning what series are. But one of the main challenges in this part of the course is to keep those two things straight. So I'll be talking a bit more about that next time. Yeah, and I guess I will see you guys on Monday.